Hi Steve. This is our overall final product, the processor, and we'll start off explaining our processor from the program counter. So when we begin our processor process, we will reset it first, so that we're sure that the initial input in this register is all like 32 zeros, and it will match with an instruction stored in the ROM, which is the instruction memory that you program in MIPS. As it is in hexadecimal, when the output from the program counter doesn't match with anything stored in the ROM, it will go in a loop that adds 4 in binary. That is 100 each time to adds up until it actually match one output. No, like match one instruction stored in the ROM. So it's actually like add 1 in hexadecimal. So
Okay, so we begin after the program counter has found an adequate address for the ROM where the instructions are being held. The ROM will output the instruction in binary, in a 32-bit binary value along this line, and each individual line here will take a certain section of that code and use it to pass the instructions. So up in the control unit, it will take the opcode, or the first bits between 31 and 26, and it will also take the func code. And here, in the control unit, it will determine what kind of function it actually is, and the outputs will just be the controlling the switches to enable this function to actually work, such as a jump function will enable a multiplexer to cause a jump, etc.
okay, under the control unit, this is the reg file, and this is controlled by 2 of the control signals. One of them is the read write, which controls that the writing function to one of the register here, and the other is reg DSC, which actually specify like which destination the register is being read. So you see like the 20 to 16 bit from the instruction memory is inputted here and here, which is read from to a register and controlled by a multiplexer right to the register as well. So it is controlled. This function is controlled by the regDSD function from the control unit. Okay, this is the component that we're especially proud of, which is the arithmetic logic unit, and it takes a 3-bit input that is from the control unit that controls the overall functionality of this whole combinational logic, and it also takes two bits of input, which are both 32 bits that will determine the output of Y, and based on the functionality here. Like I said, it will behave differently. For example, for add, it's 0, 1, 0. So 2 is 0. It gives 0 carry in, and F1 is 1, which chooses Q and E. 0 is 0, so it chooses E. So you can see that A, B, add to E, giving out E, which is Y. And here we added 0 check in order to accompany the demand of the overall processor to reach to meet the functionality of branch. So that's overall our control unit, no, ALU, and my colleague is going to talk about 32-bit adder in specific.
So this is our 32-bit adder we designed, and we're particularly proud of this part as well, because we designed it basically from scratch, and we're really happy with how it turned out, and the fact that it worked perfectly on the first try. So we're really happy with the design and everything about that. So after the reg file has stored the data, the program flows to the next part here, which is the multiplexer and the ALU. So the ALU determines the address of the instructions and the registers that the instruction references based on the inputs, and these inputs are either read directly from the registers or from this multiplexer, and this multiplexer reads this multiplexer takes from also the registers, or a sign extended part of the instruction which contains the actual value, the immediate value. So after the ALU has determined the result of the operation, it outputs it to the data memory where the addresses are stored and referenced, and the data is written to the data memory directly from the registers here along this line. And finally, the results of this is output to the multiplexer, and this multiplexer either reads directly from the ALU, the result of the ALU, again depending on the instruction, or it reads from the data memory, and this is returned all the way back to the registers again, depending on the instruction, of course.
The 15 to 0 bit of from the instruction memory actually performs the branch function here. So it has the sign extend 16-bit, and left shift 2, and then 32-bit adder. And branch function is controlled by the control unit, where if you type in BEQ, which stands for branch if equal, in the instruction memory, it will give up branch here, but it wouldn't select the value from this component unless the ALU unit is giving out 0 here. So it's when you type in BEQ here, it's actually comparing if the ALU is giving out 0 as a result, which means that the ALU control unit is giving subtraction instruction to ALU to compare the input A or B is the same. So if they are the same, this AND gate will output 1, which will select the input from this branch combinational logic function.
Okay, so once the control unit has determined that this is a jump function, it will output a 1 along the jump line, causing all of these operations here to not take place. Because once the jump function is 1, it will go down and it will select input B on the multiplexer. So B is calculated by taking the value from the ROM here, the last 26 bits, and left shifting them up to 28 bits. So once these last 28 bits are taken and added up to 32 bits by taking a value from the adder next coming from the program counter. It will add it up and it will take extra bits from the end to add it up to 32 bits. So these 32 bits will be fed into the multiplexer, and because the jump line is 1, it will select this line and it will input it into the program counter. And then the program counter will then contain the location of the next instruction and feed that into the ROM. Okay. So this is the magnitude function, which squares numbers and displays them on the FPGA. So the first line here simply initializes a register T1 to 0, and the second line initializes the register T2 to 1. Here, this line is simply a marker for our loop function, where we will continuously loop this section of code through itself. So the first line here in the loop stores a value T1 of the value of T1 in a register of this address here, which causes the display to update and display that current value, which is currently 0. The next line then adds T1 to T2 and stores it in T1. So it will simply store 1 in T1 and move to the next line here, where T2 is incremented by 2. So this loop continues back up here, and this will display 1, and this will continue on for every square number up to 4, 9, 16, and 36, etc. And that's it.
Okay, this is our, to meet the challenge, we actually create a magnitude calculator in decimal that shows decimal points. So that's the program, and for the first 8 lines, it created initial values for which I will explain later. So here comes the first loop, which is named after loop. It will T6 here is the value that we want to store in the register, which will be shown in the display. And T1 and T2 is actual like a magnitude value calculator that in which T2 increment by 2 every time we go through this loop, and T1 is where we store the value of the actual value of the magnitude, and we want to use two values, T3 and T6, as intermediate value to store the actual value of magnitude to get operations that transform the magnitude value from hexadecimal to decimal. So after we have gone through the first loop, we jump to the DEC, which is decimal loop that we have named. Here we encounter the same first function, which is set less than T4 less than T7. No, T7. Whether check whether if T7 is less than T3. T7 here is 10 in hexadecimal, which is A, and T3 is the value that we get from T1. You see here we store the value of T1 to T3. So this is actually the actual value of magnitude here, comparing to 10 to see whether it is less than 10. So if it is less than 10, it will show like 0 here. If it is bigger than 10, it will show 1 here. So if it is bigger than 10, it will jump to the subtraction function here, which is this. So in the subtraction function, it will subtract 10 each time when we go through this function, and there's a counter T5 that increment by 1 each time we go through this loop. It will jump back to DEC to check if we have subtract enough 10s to make T3 less than 10. So if we have made enough times of subtraction here, the number of times that we did subtraction will store in T5, and we will jump to count, which is conversion here. The loop conversion. So first in the conversion, we'll check if T5, the counter that we did in subtraction function here, to be 0. If not, we'll go on with function here, which add T6, that is the value stored. Now it's the value of T1, which is the actual value of magnitude in hexadecimal, and we'll increment it by 6 each time we did, based on how many times we have subtract by 10 here. So the more that we have subtract by 10, the more that we will add by 6 in T6. So once this conversion will loop until subtract T5 gets to 0, which will go back to the loop and do everything from the beginning again. That's the sample code, and we have flashed it, and we have compiled it, and now we're going to flash it. So, programmer, and FPGA is connected to this computer. It's gonna flash right now. Okay, flash successful. Yeah, you reset successfully, and then go back to 0. Okay, now we have written our magnitude code in hexadecimal onto our ROM, and we have compiled it. That's the compilation report, and we are going to flash it onto our.
Okay, so keeping power saying hexadecimal.
Okay, now we have flashed into our magnitude code that gives up power in decimal. So that's our code is common, and it's included in the symbol file. It's fully compiled, and we are going to, we'll show that it is fully compiled, this file, and we're going to flash it onto the thing. So, flash.
It'll go slower after as we go on, because it's a huge loop. As you can see, it's really fast.